So thank you all for hearing me today. I will present you our paper, who was published in IEEE in a TIFS journal in 2020. So it was a joint work between with Tomáš Pevný, Patrick Barr, and John Klein. So the paper is Explicit Optimization of a Min-Max Steganographic Game. So I will start the presentation by short introduction about what is steganography and steganalysis. And then in the two following points, I will present what are the state of the art in steganography and steganalysis. Then in the point 4, I will present our contribution. So in fact, we are playing a game between steganography and steganalysis. And very shortly at the end, I will present our current work on the most recent results we have. So about steganography. So I will present you a really short example, which is fictional. So let's imagine that we are in France in 1941, and half of France is occupied by German army. French government installs the CST, which is an organization in charge of watching French citizens through their letters correspondences. Eve is an employee of the CST, and she opens the letter, and it's Alice writing to Bob, and she asks him to give her some advice about a music she wrote. So here's the music sheet who was attached to the letter. Okay, so Eve doesn't think it's a suspicious communication. So in fact, she doesn't know anything about music. So she closed the letters and she sent it to Bob. But in fact, Alice and Bob previously agreed about decoding method. So each note in the music sheet was preceded by a flat or sharp symbol, in fact, was linked to a letter of the Latin alphabet. So when he follows this rule, he can read a secret message in the music sheet. So the secret message is attack leave. So he understands that his security is at stake, so he leaves the country. So this was an example to address you the three characters in a general steganographic and steganalysis scheme. So we have Alice communicating to Bob through an open and public communication channel. And there is Eve, the steganalist, which is very powerful because she has the power to cut the communication. We are in a case where Alice, in fact, wants to communicate a secret message to Bob. So her only solution, because Eve doesn't want them to communicate secretly, Alice wants to really be not suspicious. So she will have to hide the secrets in the communication, such as the communication looks legitimate. We assume that Alice and Bob can previously agree about a decoding method, and they can share a secret key. So we have here two opponents, which are Alice and Eve, because they two have really antagonist goals. Okay, one more thing is that our work relies on the Carcass Principle. Firstly, this principle was introduced in the context of cryptography. It was translated here to steganography, where in fact we assume that Eve knows everything about Alice's strategy except the secret key. So it means we want is to make sure that the security of the steganography scheme doesn't rely on the secrecy on the method. So we assume that Eve knows a lot of things, so it's kind of worst case scenario. Okay, so that's it for the introduction. So let's dive into how to handle today what are the state of the art about steganography with here digital images. So we'll imagine that Alice wants to communicate to Bob through images. So how to hide a secret in digital images? So a way to do that is by cover modification, where cover here stands for original image. So Alice will modify some pixel of the cover by really a small modification, so -1, 0, or +1, such as we are not too far from the original image, but such as she can embed the message. So the most straightforward way to do that is by Lsb replacement. So where Lsb stands for least significant bits. So for here we have an image X where each pixel is coded on 8 bits. The Lsb is here in red, so it's the bit containing only the information about parity of the pixel. Lsb replacement just consists in replacing all the Lsb of pixel by the message bits, such as each pixel will embed a bit of the message, and such as we embed a message in the image, and we have a stego at the end, a stego image Y, which is not too far from the cover image. But we still need to be very careful because it might be really detectable to do that. So to explain that, here the cover, and here the Lsb of the cover. So we have only two possible values, 0 and 1, 0 and 1, or 1. So that's why there are two colors here, black or white. And you can see that in fact the representation of Lsb in this cover is not random. So you can see there are some patterns and there are some areas where there are a lot of Lsb equal to each other. So if we do dumb Lsb replacements, we'll destroy all those statistical features. And in fact, we can trust me that this will be very, very detectable. So this is really the basic problem of steganography. And how to solve this problem, first idea is to decrease the size of the message. So we don't want anymore to embed 1 bit of message into each pixel because it's too much. The second idea is to adapt the embedding to the content of the image. So we don't want to destroy the statistical features. So we want to avoid, for example, those areas, and maybe more embed on those areas which seem already random. So to do that, to adapt our embedding, we will, in fact, assign a cost to each pixel. So this is a very classical technique, where to each pixel Y, we'll assign 2 costs of modification, -1 and +1. So finally, we have which name is a cost map, so the set of cost of modification of the cover image. And in practice, those cost maps are heuristically computed. So for example, here an algorithm which assigns to the cover a cost map of modification. So I say that it's computed by heuristic because it was to compute those cost map, you just filter this image with high pass or low pass filters, such as it does what we hope it will do, what we have the intuition that it does. So that it will assign high cost of modification in here, smooth areas, so here blue, and lower costs in areas which seem less dangerous. Okay, so now that we has linked a cost of modification to each pixel, we need still to embed the message. We want Bob to be able to decode the message. So how it is usually do, again, we assume that Alice and Bob previously share matrix H. So they both have this matrix. And the decoding method is simply that multiplying the stego image to obtain the message M. So from Alice's side, she needs to design a stego, such as it respects this equation. In general, so the size of the message is way smaller than the size of the image, so the number of pixels. So here you have a system of equations with way more unknowns than equations. So finally, it gives, in fact, Alice freedom to design Y, such as it will minimize the cost of modification. She will adapt, she will choose the best stego which respects this equation, which in fact minimize the cost of modification. So you have two independent tasks here. You have, from Alice's side, you have the first task of designing a good cost map, and the second task to really embed the message while respecting this cost map. Here we are only interested really in the design of the cost map, as we will see later. So this second step, we are not really embedding the message. I mean, in fact, we will simulate the embedding. So we will simulate an optimal embedding, and it's nice to do that because we have a nice result. We have a theorem that gives the distribution of stego which achieve this optimal embedding. This distribution of stego is given, can be computed with the cost map, of course, and with the size of the message. So finally, when we simulate embedding, we have this very general and very important pipeline here. So on the left, you have your cover image. You can compute with the technique you want, the cost map of modification. And after, you will simulate the probabilities of change according to the theorem. So, such as it will simulate the optimal embedding. And after, you just need to sample according to those probabilities to get a stego image Y. So for example, here, I plotted again the two, so the cover image and the cost map you previously seen. And at the end here, for a given size of the message, I plotted the probability map. So you can see that you have it's kind of the opposite of the cost, where you have very low probabilities of doing change in the sky, and you will hide here more the secrets in the castle. Okay, so that's it for steganography with digital images. Now let's see how to do steg analysis. So the goal of steg analysis, the goal of Eve, is really to detect the presence of a message. So it's to say yes or no, it's this binary information, if a message has been hidden and if the cover doesn't look like a cover. So in fact, Eve needs to build a classifier to distinguish between cover and stego images. The best techniques to do that today are achieved by CNN, so convolutional neural networks. So you will see later those notations. So those XU-Net and SR-Net are two famous in the domain of the steganography, are two famous tools to achieve steg analysis. And for the notation, you will see F, which stands for a classifier, which takes in input an image and outputs a real number between 0 and 1. And we assume that the decision threshold is 0.5, and if the output is below, we have the image is classified cover, and vice versa. Okay, so now comes our contribution. So you see that you have two opponents. So Alice wants to design the best cost map, while Eve can always construct a new classifiers to try to detect the stego which was produced with this cost map. So I will first introduce this game with the game theory vocabulary. So we have two players, Alice and Eve, indexed by A on E. I note like that the action of both players and their utilities function. What are the actions? The action of Alice is all the embedding function which maps a cover to a stego image. And the action of Eve are all the classifiers in a set F, which classify an image and outputs this real number. The utilities, so let's first say the utility of Eve. Eve wants to detect the presence of the message with high accuracy. So her utility is the accuracy of classification. So this sum of two terms where she wants to correctly detect cover and correctly classify stego. The utility of Alice is here the opposite of Eve's utility, logically, because she wants that Eve mistakes the most as possible because she doesn't want to be detectable. So with those notation, we, in our paper, we introduce this goal where we want to Alice to achieve the best embedding, detecting the best classifiers of Eve. It's why here we have a first max step amongst all action of Eve. And then we have the outer minimization where Alice wants to optimize with respect to the best classifier. But in practice, this is really difficult to achieve. One reason is that both of those sets are really, really huge. So we proposed to approximate this game by an iterative strategy where Alice and Eve will play we play one move in each iteration of this iterative strategy. So what are the two steps in each step of the iterative strategy? The first, so it's the move of Alice. We assume that Eve has a finite set of function, which is not too big, and Alice will try to defeat the best classifiers of Eve. So here we will place all the big set of Eve action by this smaller set. And then it's Eve's turn, and she will try to detect the just created stego of Alice. Once she created it, she will append it to her set of classifiers. So at the next step, Eve will have one more classifiers in this set. Now I will precise how to do that, because it's not that easy, because I recall that we are doing Steganographic. So in fact, we want to do that by replacing the cost map. So the practical solution, so we want to optimize the cost map with respect to the outputs of a classifier. So rho with respect to f of y. So what we would like to do is to compute the gradient of fy with respect to the cost map, such as we could be able to apply, for example, SGD. But in practice, it's not easy, because I recall that we had this pipeline. At the end, you have the evaluation by the classifier. So in fact, this step is not differentiable, because this step, it means that you will sample according to those probabilities and add some discrete change to the cover image. So to fix this problem, we use the state-of-the-art, so an algorithm named adversarial embedding. And this paper proposed an heuristic to update the cost with respect to the gradient of the classifiers with respect to y. So because we can't backpropagate through all this pipeline, we are stuck here. We only will use this gradient to update the cost. So just so you understand, here, for example, the how to update the cost of doing +1 according to the sign of the classifier. So you will multiply or divide by some constant the cost, such as you will have an adversarial impact of the output. So this is a way to achieve this action. So by updating this cost map by this way, you will produce a stego which have an adversarial impact of the outputs. And then you just need to do that for each classifiers and apply a min-max strategy. Then for the second step, Eve just needs to train a new classifier, because I recall that she trained CNN. And she will train the classifiers, train to detect the just previously produced stego images. Okay, so now the results. So how to read our graphs? So on the x-axis will be shown the iteration. So it's discrete steps. Because you know it was an iterative strategy, so we did of this iterative strategy. On the y-axis will be plotted the error rate of classifiers of Eve. So it's the error rate of the classifiers trained in this second step. Note that the first iteration, so iteration 0, is the state of the art. So it's the error rate given by classifiers trained to detect the heuristically computed cost map. Then all further iterations are our contribution. Each step is from our iterative strategy. Another subtlety here is a match about assumed Eve's action and real Eve's action. Because when Alice trying to defeat a classifiers by this min-max step, she's assuming Eve's action. So we not like that assume Eve's action and with a tilde, so real Eve's action. Because in fact, we wonder if there is any problem where those two sets are different. So you will see that during the protocol, Alice will optimize herself against assumed Eve's action, and we will add more Eve's action to see if we are still defeating the real Eve's action. So here's the results. So I will start with the plot at the left. So you have here the real Eve's action is the XU-Net architecture. So it's a classifier that Eve has. And then there are 3 more classifiers in the real Eve's action. So when there is no mismatch between the two, so when here it's for XU-Net, because this architecture is in the both sets, it's a plain line. And what you can see is that, in fact, we are succeeding into optimizing against Eve. For dashed line, when there is a mismatch, when Alice didn't expect Eve to act like that, we are still, in fact, improving ourselves. So what's important is the difference between further iterations and to compare it to the state of the art, which is achieved at iteration 0. We have here another example where we replace XU-Net by SR-Net. So we optimize, Alice optimized herself against SR-Net. And what you can see is that, again, we are not as good against XU-Net because there is a mismatch, but we are still improving ourselves. Okay, now let's talk about our current work. So our philosophy is trying to removing at most all the heuristic in the scheme. So we were annoyed because in adversarial embedding, there was this heuristic to update the cost with respect to the gradient of the classifier. So we looked a bit in the literature of machine learning, and we discovered that there was this solution to approximate discrete change by smooth changes. So such as, so here I will note the smooth change by a tilde. And what is nice is that it's now a backpropagable step, such as now we can compute the gradients of the output of the classifier with respect to the cost map. So the solution we used was the approximation of the categorical random distribution by a softmax Gumbel distribution, which was controlled by a temperature tau. So now the results again. Here we have a third architecture of the CNN, and we are trying to optimize with respect to the 3 classifiers. And what we can see is that we are reaching again good results into improving the steganographic scheme, even against non-targeted classifiers, which are again in dashed line. So yes, so what's here important is all the improvements. So plus is the difference between the 5th iteration and the initial iteration. And for here is in bold because there is no mismatch. So we are really optimizing against those classifiers. So finally, to conclude, we produced an iterative protocol in order to automatically play the game. Because before, how steganography and stegananalysis worked, there was every 2 years a paper about a new heuristic about producing a cost map, or a new way to detect, so from Eve's side, to detect this cost map. So it was a mouse and cat game which evolved, and we tried to automate this protocol by, and it produced cost map which improved by themselves, so which automatically play the game. Okay, so thank you very much for hearing me, and I'm ready to listen to your questions.
Thank you, Solène, for a presentation.